In this course, we'll be discussing transcendental functions, exponential functions and their inverses, the log functions, also the trigonometric functions and their inverses. So let's start off with our exponential function. The basic form is f of x equal a to the x. The base a must be some real number greater than 0 and not equal to 1. And x can be any real number. So the domain of our exponential function would be all real numbers. Here's a little bit more general form for an exponential function. We have f of x equal to c times a to the x. C is a kind of a coefficient of a to the x. And we say c then is the initial value of the function, because when x is equal to 0, you see that f of 0 is equal to c times a to the 0. And of course a to the 0 is equal to 1, so then that's just a to the 0 is 1, so we end up with our initial value being equal to c. The base a is called the growth factor, okay? And of course, if a is a number greater than 1, then the function will be an increasing function, and we can use it to model things that are growing larger as time goes on. As x gets larger, then a to the x is getting larger. So it's an increasing function. We have a theorem that says that the ratio of f of x plus 1 to f of x is equal to a. Well, let's simplify the fraction that we have here. We can cancel c in the numerator and denominator, and then rewrite the numerator as factors a to the x times a all over a to the x, and now a to the x will cancel, and we just end up with the ratio equal to a. So when we increase our exponent by 1, we multiply our function by 1 factor of a. Now let's think about the graphs of f of x equal a to the x, particularly when a is something greater than 1. Okay, if we do a little graph, we can see the domain and the range quite easily. Turns out the domain will be all reals. We said that x could be any real number. And y, it can only be positive real numbers. So the range is going to be from 0 to infinity. So here's a graph. Say when x is equal to 0, y is equal to 1. When x is equal to 1, y would be equal to a. And when x is equal to negative 1, y is 1 over a, which would then be a fraction between 0 and a. And here we have our increasing function. Now notice as x is getting smaller and smaller, so as x is going toward negative infinity, it turns out that y is getting closer and closer to 0. And so that defines what we call a horizontal asymptote. In this case, it is the x-axis, which is the line y equal to 0. The graph is continuous and smooth. It is a one-to-one function. In other words, it passes the horizontal line test, and so it will have an inverse function, which in fact will be the log function. Now the graph of this exponential function y equal a to the x, when a is between 0 and 1, will be a decreasing function. So when x is equal to 1, we have y equal to a. Now a is between 0 and 1, so it'll be something less than 1. And then when x is minus 1, a to the minus 1 would be a number larger than 1, so we can kind of estimate it there and draw our decreasing function. And the point over here is minus 1 and 1 over a. Again, the domain is all reals. The range is from 0 to infinity. Notice that as x gets very large, and then we'll notice y is getting closer and closer to 0. So we have, again, a horizontal asymptote, which is the x-axis or the line y equal to 0. And these are one-to-one functions. They're smooth, continuous. They pass what we call the horizontal line test, and so they will have inverses. Okay, so the inverse function exists. And here are two exponential functions. The first one on the left has a base greater than 1, and it will be an increasing function. When x is 0, y is 1. When x is 1, y is 4. So we would have the function going up like so. And the function on the right will be a decreasing function. When x is 0, y is 1. When x is 1, y is 1/4. And when x is minus 1, y will be 4. So here is our decreasing function. Both of these functions have the same domain. They have the same range. Zero to infinity, and they have the same horizontal asymptote, which is the x-axis or the line y equal to 0. Notice this function on the right can also be written as 4 to the negative x. which is simply a translation or a reflection of the original graph, okay, across the y-axis. And you can see that the graph is in fact a reflection of this first graph across the y-axis. Here are two more transformations of the graph y equal 4 to the x. The one on the left here will take the graph up by 1, up 1 unit, and this graph is going to take the graph of 4 to the x left 1 unit. So on this side, when we go up, the horizontal asymptote will also go up to y equal 1, and our range will be from 1 to infinity. Whereas the graph on the right here will have the same asymptote as just 4 to the x, y equal to 0, with the range from 0 to infinity. So here's a graph up 1 unit. So here's our horizontal asymptote, and for the x would be increasing graph. On the other hand, if we go to the left 1 unit, our y-intercept would be at -1, and so we cross the y-axis, our y-intercept moves to the left by 1, and our y-intercept then becomes 4. So when x is 0, y would be 4. Here are two more transformations. On the left we have a vertical stretch by a factor of 3. So when we put in x equals 0, we get 3 times 1, or 3. And when x is equal to 1, we have 3 times 4, which is 12, a vertical stretch. On the other hand, when we have a minus sign in front of the exponential function, it reflects the graph over the x-axis. So it's a pretty dramatic change. When we put in x equal to 0, we will have a point at y equal -1. When x is equal to 1, y will be -4. So we have this decreasing function now. And the range has changed. It is now from -infinity up to, but not including 0. And of course the horizontal asymptote in both of these graphs is the line y equal to 0, or the x-axis. But here the range is from 0 to infinity, and on the second graph the range is from -infinity up to 0. Now if we take the limit as x gets bigger and bigger of this expression 1 plus 1 over n to the nth power, we will approach a number we call e, which is approximately equal to 2.718. And this is an irrational number. It's non-repeating and non-terminating decimal. We use e for many of our applications. So let's do a graph of e to the x with a transformation on there. Y equal minus e to the minus x. In fact, we have two transformations here, a negative in front of the e and a negative in front of the x. So to plot a few points, let's put in 0 for x, and we will get e to the 0 with a minus sign, so that's going to be minus 1. If we put in minus 1 for x, we'll just get e to the x with a minus sign in front, so that's negative e. And one more point, if e is equal to 1, if x is equal to 1, we'll get minus e to the minus 1, which is minus 1 over e, or approximately minus 0.37. So our graph is a transformation across the x-axis and across the y-axis. So that's going to be as follows. At 0, we'll have a point at negative 1. At minus 1, we will have a point at minus e, so that's approximately minus 2.7. And at x equal 1, we'll be at approximately minus 0.37. So here's a graph, turns out to be an increasing function now, with domain all reals, and our range from minus infinity up to 0, and horizontal asymptote at y equal, or is y, the line y equals 0, which is the x-axis. Because the exponential functions are 1-to-1, we know that if a to the x power is equal to a to the y power, then the exponents x and y must be the same. We can use this to solve some equations. If we can get the same base on the same side, same on both sides, we can set the exponents equal to each other. So here's an example. We have 5 to the x power times 5 equal to 1 over 125. Well, we know that 125 is equal to 5 to the negative 3. So we make that substitution on the right. And then to multiply these two factors, we add the exponents. So we'll have 5 to the x plus 1. Then we can set the exponents equal to each other. X plus 1 is equal to negative 3. Subtract 1 from both sides, and x is equal to negative 4. So our solution set for this equation that we started off with, here's our equation, our solution set is negative 4. Here we're asked to find the real zeros of this function, f of x equal 1/3 to the x power minus 9. Well, real zeros is another term for the x-intercepts. So to find x-intercept, we set y equal to 0, and we'll solve then for x. We'll add 9 to both sides. And let's try to get the same base on both sides. So shoot for 3 squared on the left, and 3 to the minus x on the right. Set the exponents equal to each other. Multiply by negative 1. And we have our solution here. X is equal to negative 2. The next transcendental function that we'll study are called logarithmic functions. The form of that function then, y equal log base a of x, and that is equivalent to the statement a to the y is equal to x. In other words, the value of the function, the log function, y, is actually an exponent. The base of the log must be a number greater than 0 but not equal to 1, and the argument x must be something that is a positive real number. Now this is an equivalent statement, a to the y equal x. So we're able to write statements such as log base 4 of 64 is equal to 3. We can write that statement in the exponential form. 4 to the third power is equal to 64. These again are called equivalent statements. We could take a more general form. 3 to the p power is equal to k. Now this is your exponential form, and we can write that in logarithmic form. Log base 3 of k is equal to the exponent p. And you'll want to be able to switch back and forth from exponential form to log form, or from log form to exponential form. Now let's use that as a strategy to evaluate the expression log base 3 of 1 over 81. So first set this equal to y, log base 3 of 1 over 81, and then change it to the exponential form. 3 to the y power is equal to 1 over 81. Well, we can change the right side to an expression, an exponential expression with a base 3. 3 to the y is equal to 3 to the negative 4. Well, now we have an equation, the same base on both sides, so set the exponents equal to each other. And we have the value of our expression. It's equal to negative 4. So here we have log base a of x equal y is equivalent to a to the y power equal to x. If we switch the x and the y in our exponential form here, what we will find is the inverse of our log function. So our inverse then is in fact an exponential function, y equal a to the x. So recall that the domain of the log function will be the range of the inverse function, y equal a to the x, and that range is from 0 to infinity. So that will be the domain of the log function. The range of the log function will be the domain of the exponential function. The exponential function had range from domain from minus infinity to infinity. So that becomes the range of the log function. So let's write that down. We have y equal log base a of x, and it has domain from 0 to infinity. and range from minus infinity to infinity. Another interesting characteristic is the relationship of the asymptotes. We have a horizontal asymptote for the exponential function, and it was the x-axis, or the line y equal to 0. But we'll see when we graph the log function, the domain of which the domain is from 0 to infinity, it has a vertical asymptote, and it is the y-axis. The equation for that is x equal to 0. To find the domain of a log function, we want to guarantee that the argument, whatever we're taking the log of, is something that is positive or greater than 0. For example, if I have the function y equal log base a of x over x minus 2, then x over x minus 2 must be greater than 0. Well, this is solved as we would solve a rational inequality. We find the cut points by setting the numerator and the denominator equal to 0. So x equal to 0 from the numerator, x minus 2 equals 0, x equal to 2 is the other cut point. So on the number line, we use our cut points to divide the number line, and then we test a number in each interval using our expression x over x minus 2. So we'll test any number in the first interval, say x equal negative 1. Negative 1 over negative 3 would be positive. We put in, say, x equal 1, that would be in the second interval. That would be positive over negative, which would give us a negative result. And in the third interval, let's use x equal 3. Positive over positive would be positive. We want the expression to be positive, so we're going to choose the first and the last interval as our solution set. So we can say the domain of our log function is going to be from minus infinity up to 0, not including 0. And then we'll pick up on the other side of 2 and use that second interval, and we get our domain from minus infinity to 0 and from 2 to infinity. So numbers in those intervals would cause our argument to be something greater than 0. If we chose a number between 0 and 1, I'm afraid our argument would be less than 0, and that would be quite impossible. And one of the logs that we use in many applications is called a common log, which has a base 10. And when you see the log written without any base shown here, then you know that it is specifying base 10 with, so log of x is really log base 10 of x, and that will be on your calculator. We want to do a quick sketch of this graph, so let's switch or change to the exponential form, and that would be 10 to the y is equal to x. We'll plot just a couple of points for this graph. I'm going to put in values of y and get values of x. So when y is 0, x is 1, and when y is 1, x will be 10. Well, we know that the domain of this log would be from 0 to infinity. So there will be a vertical asymptote, and it is the y-axis, which is the line x equal to 0. So knowing the vertical asymptote and a couple of points, we can do a graph of the common log. So here's our vertical asymptote, the y-axis. We can go over to 1 and 0, and then over to 10 and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 1, and so we have an increasing very gradually, going through the point 10 and 1, and of course 1 and 0. We also use base E for logarithms, and when we use base E, we usually just write the log as ln of x with no base indicated there. So ln means that the base of the log is E. Remember, E is approximately 2.7. The equivalent statement, e to the y equal x, will help us to plot a few points. We know that the domain is from 0 to infinity. And so we have a vertical asymptote, which is the y-axis, or the line x equals 0. So with these 2 points that I've figured using our exponential form, we can plot this graph. We go over to 1, okay, and then over to E, which is approximately 2.7, and up to 1. So we have the graph of the natural log of x. Goes up a little more rapidly than the common log does. Now notice if we switch the x and the y on this exponential form, we will have the inverse function for the natural log. So switching x and y, we have inverse function so y equal e to the x. Okay. So let's plot that. And we can simply switch the coordinates on the log graph, the natural log graph, and we will have coordinates, instead of 1, 0, we'll have 0, 1. And instead of E and 1, we'll have 1 and E. So over here, here's our plot. And over to 1 and up to 2.7. About so. And you'll see that this is a reflection of the original graph across the line y equal x. I'll plot that up through the origin. So here's the line y equal x. And the inverse function is just a reflection across that yellow line, y equal x. And we found it simply by switching the coordinates on the natural log graph and replotting them to get the exponential function y equal e to the x, which is the inverse of the natural log of x. Now let's do a transformation of a log graph. Here we're going to do a common log graph with the argument x plus 2. Now that's in parentheses, so we know the graph is going to be translated to the left by 2. To get the domain, x plus 2 greater than 0, x greater than minus 2. Okay, so then we know we have a horizontal asymptote, a vertical asymptote. The vertical asymptote is the line x equals to negative 2. So we've got the vertical asymptote. Let's change this to the exponential form and plot a couple of points. From that, our exponential form would be, let's start off with y equal to the common log, x plus 2, and change to the exponential form, 10 to the y equal x plus 2, and subtract 2. Okay, so we'll just get a couple of points here. Plugging in things for y to get x. So if I plug in 0 for y, I'll have 1 minus 2 or negative 1. And another easy value would be 1 for y. That would be 10 minus 2 is 8. So with these 2 points and our vertical asymptote, I believe we'll be pretty good shape here. So okay, so 1, 2, we've got a vertical asymptote. X equal negative 2. And the point at minus 1, 0, and at 8 would be at 1. 1, 2, 3, 4, 6, 7, 8. So I think I wrote that backwards, 8 and 1, beg your pardon. So here is our graph of the common log of x plus 2. Now we might as well go ahead and plot the graph of the inverse function. So I'll change to red here. And just switch the coordinates that we have on each of those points. Minus 1, 0 becomes 0 and minus 1. And 8 and 1 becomes 1 and 8. I'll just kind of estimate where that would be. And because we have vertical asymptote at x equal minus 2, we'll have a horizontal asymptote at y equal minus 2. So then our exponential function, which would be the inverse of the log function, will be an increasing function. Like so. So I'll write that function in red. That would be y equal to 10 to the x minus 2. And that is the inverse function of the log function, so we might as well use the inverse function notation. So our f of x is equal to log, common log of x plus 2, and our inverse function is 10 to the x minus 2. Here's another transformation, this time of the natural log of x plus 2 is not in parentheses, so it indicates that we're going to go up 2 units. Now our domain is determined by the argument x greater than 0. So then we have a vertical asymptote then, and it is x equal to 0, which is the y-axis. Now to get a couple of points, again, I'm going to change this to the exponential form. Y equal natural log of x plus 2. I need to isolate that log so I can switch to the exponential form. So y minus 2 is equal to the natural log of x. And the exponential form then becomes e to the y minus 2 is equal to x. We'll just get a couple of points because we already know the vertical asymptote is x equals 0. So an easy number to put in for y would be 2. 2 minus 2 is 0. E to the 0 is 1. We can put in y equals 3. 3 minus 2 is 1. And we end up with just x equal to e, which is approximately 2.7. So here's our graph. Go over 1 and up 2. And over to approximately 2.7. And up to 3. And here is the graph of our function, our natural log of function of x plus 2. So you can see the graph has been moved up by 2. So let's graph the inverse also in a different color. So we'll replot these points. Instead of 1, 2, we'll plot 2, 1 over 2 and up 1. And over to 3 and up to 2.7. Now where we had a vertical asymptote of x equal 1, we'll just use the y-axis. For a vertical asymptote, the horizontal asymptote would be the x-axis, so we'll be coming up from here and going up this way. Now the green graph then is the inverse function, and that inverse function can be written by switching the x and the y. So the green would be f inverse of x, and it's going to be e to the x minus 2. So that's the inverse function of our natural log function, natural log of x plus 2. Okay, let's use some properties here to solve this equation for x. X is the base of the exponent. So let's immediately switch to the exponential form. X squared is equal to 36. Take the square root of both sides and we get x equal to plus or minus 6. But remember, x must be something greater than 0. The base of the exponent has to be something positive. So we can't use the negative 6 as a solution. So we only have one solution here, which is positive 6. So when you are solving equations with logs in them, you have to be sure that the base of the log is going to be something that is positive. Also, the argument of the log has to be something that is positive. Now here's an exponential equation, and we might be able to solve it by using logarithms. So in order to switch to the natural log, I have to first isolate my e to the 2x. So divide by 3 first. So e to the 2x is equal to 10/3. And then we can change that to the natural log form. So the exponent 2x is going to be equal to the natural log of 10/3. So then we just divide by 2 or multiply by 1/2, however you like to do that. And we have isolated the x. Now this is called an exact answer here. But if we want a decimal approximation, we can simply put all that in our calculator, and x is approximately equal to 0.602. Again, this is the approximate value. The exact value is 1/2 times the natural log of 10/3. Now here's an application of an exponential function. It is a model r equal e to the kx. And we know that x stands for the blood alcohol level in percent. And when that blood alcohol level is 0.02%, we know that the relative risk of an accident, a car accident, would be 1.4 times as great as it would be if you had no alcohol in your blood. So the model has a constant k in there, and we'll use these figures up above given to find k, and then once we find k, we can use that model to find values of r or values of x. So substituting in 1.4 for r, and for x, we'll put in for x, we put in 0.02. That corresponds to the relative risk of 1.4. We can immediately change it to the natural log form. Natural log of 1.4 then is equal to 0.02K, and divide both sides by 0.02, and we find K, constant K, is equal to the natural log of 1.4 divided by 0.02. This is approximately equal to 16.82, which you can find on your calculator.